Well, okay. Let's see. Now, this afternoon, I thought I would, since we're kind of at the end of the course, I thought I'd do a little bit different thing. And I'll review the nonlinear regression again, if you like. Which, the way I brought it up last time was as a streamlined or kind of a unified way to have done the estimation of the exponent alpha for the regression function in the windmill data, example 5.2. Remember, I don't know if you remember that, but there was some kind of regression function we had introduced, and I remember that the author actually computed the estimate wrong. Okay, he said, well, it looks like the DC power output or DC power output, that's what it was, of this windmill had kind of an asymptotic upper asymptote. Well, that was okay, but the question was how fast did how was the asymptote being reached? You know, some negative power of x we presumed was involved with an upper asymptote beta 0. So we had assumed, well, it would be beta 0 minus a beta 1 x to the minus alpha for some alpha greater than 0 for the regression function, something like that. Okay, well then miraculously the estimate came out to be alpha equals 1 okay, by the author's method, and there was a flaw in his calculations. Now, I didn't actually redo the calculations with the streamline method. If you like, I can do that for tomorrow, or we could try to hack through it today if you want. So that was example 12.2 that we considered was the Puromycin data. So how do you actually do nonlinear regression? The basic formula that was a unification of the method we used in Chapter 5, which was giving us something, was as follows. The nonlinear regression, let me just do a real quick review of it. Then you have y is some function of x in some parameters. Well, let's just call them theta 1 and theta 2. And theta maybe, and some more, maybe theta 3 or something like that. Okay. Which in our case for the windmill data was theta 1 was equal to beta 0, theta 2 was equal to beta 1, and theta 3 was equal to alpha. Okay, and I have the regression function f of x equals f of x and theta equals beta 0 plus beta 1 x to the alpha. That's what we were considering there. Okay, so this is the windmill example. Okay. So here's the general format. Y equals this plus an error. And we argued last time why you want to consider nonlinear regression instead of just doing some transformation to the regression function. In many cases, the regression function itself, you can transform and get some kind of, and you transform the variables as well, and you get some kind of linear model. But that doesn't preserve the linearity of the errors. Okay, that is the additive nature of the errors. So then that's why we go back to nonlinear regression. And so the basic thing the basic Taylor series approach was to say, okay, if I have an initial guess, theta 1, 0, theta 2, 0, and theta 3, 0, that's my initial guess of what the actual parameter theta is that I should be doing. And the whole point is to estimate theta. Theta 1, theta 2, theta 3. The whole point is to estimate theta, and in a good way. Okay, so you can state some nice properties about it. This is some initial guess. Then maybe I can get a linear model by doing a Taylor expansion, and that I could do. So x is just my variables. It could be more than one variable. It might just be one single variable. depends, but that's just sort of your x data. And then I have my new guess, my updated value will be here. Now, if I take the difference of those two, then I can expand this difference, this increment of f, as a function of the thetas in terms of a first-order Taylor's expansion. In other words, the partial derivative of f with respect to theta 1, this is going to be evaluated at the theta naughts. I'll just put it as theta naught vector, okay? At the 0th value of the vector, times theta 1 minus theta 1 naught, plus, I won't put the summation sign because that's going to be, I'll just write it out in full, d by d theta 2 evaluated at theta naught, and of course at x as well. Whatever x, but x is frozen through this whole business. Times theta 2 minus theta 2 naught, plus the partial derivative back to theta 3 evaluated at theta naught and x, and times theta 3 minus theta 3 naught. Okay? So now what you have is something that looks kind of like a possible linear regression analysis. What you'll do is you'll take, instead of the updated value of the function, you'll just plug in the y here. Okay? You just stick in the y, whatever your y data is for this, in place of this, and then of course that will make an extra error on the right hand side. Of course there's already an error because this is approximate. But so, by waving your hands in this way, it gives you a reasonable method. Because now you just have coefficients. You just have this the author calls beta 1. Okay, the increment of the theta. From the theta naught to the theta 1 sub naught to the theta 1. He calls that beta 1. He calls this beta 2. And he calls this beta 3. Or maybe he uses a different indexing, like, I forgot if he uses 0, 1, and 2, but that's what he's calling this. This basically, that's a parameter now, the increment in the theta. And then in here you just have some estimated theta naughts, and you have the x involved. Okay, in here. So x is involved in here. So this is your variable 1, this is your variable 2, and this is your variable 3. He calls this z1, or I think I might have called it z0. All right, because it's the first one, and usually, anyway. So I might use a slightly different indexing. But of course you want the betas to match the variable names. So actually the way this works out is that as I showed in the notes for the windmill data, the power alpha naught comes into the definition of the third of these variables. Okay? And even the beta 1 naught comes in to the definition of the third column. I believe in the notes last time we had that for the windmill data, it came out that we had that Z3 was equal to I call it Z2 because I had the intercept, because it was natural to call, because the theta 1 corresponded to the beta naught, it was natural to call this the corresponding intercept variable Z0. So I call it Z0, Z1, and Z2. Let me go to the book, whether they use beta naughts or beta 1, whether he uses the naught. I think he does use naughts. Let me see. Let me double check. And this is chapter 12. I don't want to be confusing you, so I'm going to change it now if it is confusing. Yeah. He's using beta naught and beta 1, and theta, but he's using his thetas as theta 1 and theta 2. So he's calling this beta naught, okay, and Z naught. He's calling this Z1 and beta 1. This is consistent with my notation. And then he's going to Z2 and beta 2. All right, yet the thetas are still theta 1, theta 2, and theta 3. So that's a bit confusing. Okay? The thetas are in one index up. Okay? So then Z2, the third Z, corresponding to the alpha power, all right, in the derivative, is beta 1, 0. I'll just use the original parameters here. Of course, a different beta 1, not those betas. That's really confusing. Maybe we should call these B's. I'll just call these B's to not confuse it with the windmill data. All right? Let's call this B0, B1, and B2. All right? For the increments. And then Z2 is beta 1, 0 log x, x to the alpha 0 is the way it came out to be for these parameters. Okay? So these are where theta 0 was equal to beta 0, 0, beta 1, 0, and alpha 0. In my worksheet, I don't refer to the betas. Okay? In my notes, in fact, I just call them coefficient of the regression of this vector. So I have that y minus f0 is approximately this, okay, plus error. Where f0 is equal to this, evaluate the regression function at the initial guess. Then, of course, you're going to update it. Okay? Where f0 is this. So let's have a look. So that's what I'm going to do. I'm going to regress I'm going to define these new variables. Sort of like in weighted regression, only it's a different method. Okay? You're defining new variables, Z0, Z1, and Z2. Then you're doing no intercept regression on them. But what you're getting for the coefficients for those variables in the output, where all the t-statistics lie and stuff, is these increments. So then you add those increments, the B0, B1, and B2, to the theta naught. So then you're going to take the theta 1, 0, and you're going to add B naught, and that's going to be your theta 1, 1, okay, equal to that. Then you're going to take your theta 2, your first iteration estimate of theta 2 is your initial guess of theta 2 plus the second increment, okay? So the indexing is a bit screwy because of our, love of the intercept, okay? Always going back to the intercept and so on and so forth, okay? But these are the increments after you've estimated them. So you're going to estimate these. These are the estimated increments. So I could put these as hats if you want. Okay, now, okay? So hopefully this is going to work. Okay? That's the idea. So instead of regressing y on something, you're actually regressing a residual. This is like a residual that you're regressing on something. But it's not the final answer. It's like you're going to do successive approximations of what the residual should be. So you're going to do y minus f0 on this, get some increments in the thetas. Then you're going to update theta and get your new fit. So f for fit, if you like, too. Also for regression function. So this is the fit, the 0th order fit. This is, okay? The F0. So let's see it. In the Puromycin data. In the Puromycin data, let's go ahead and look at that. That was the example one more time. I did go over it last time, but it was kind of hurried. So what this is showing, actually, back to the windmill data, is that the way we did it there was kind of screwy and ad hoc, and we ended up doing 2 regressions to get the next alpha, because then we said, okay, somehow we figured out what alpha should be by doing this regression, one regression. Then we went back, plugged that alpha in, and went back to the linear model, beta 0 plus beta 1 x to that alpha, and then got new betas, and then did the whole thing again, the way we were doing it. So there were actually 2 steps, whereas this actually just updates all 3 at the same time. All 3 parameters. So there's no... That was definitely an ad hoc approach that was being done back there. And we were regressing y on things. That's why we weren't regressing y minus... We weren't regressing the residual on things. Okay? If you go back and look in Chapter 5. So I don't know how I handle Chapter 5 again after I know this. Okay? I guess I do it the same way I did this one. Just do it the ad hoc way and then fix it again at the end. Only fill it in with another possible way to do it. So you could maybe introduce nonlinear regression right then and there. I don't know. Okay. So with the Puromycin data, you have a regression function of the form f of x and theta 1, theta 2 is equal to theta 1x over x plus theta 2. And Engel here, one of the graduate students, was familiar with this from actual biochemistry. Actually studied this model. Okay? And this had to do with the velocity of a certain enzymatic reaction. Okay, so enzyme was helping some biochemical process to happen, and they're looking at the velocity of that reaction as a function of the concentration of the substrate. Bring me a biochemist to tell me what that means. Okay, but we can deal with it. Okay, so there was some nonlinear model. Now, it turns out that this regression function was linearizable. So if I take y equals this without the plus epsilon, then I can transform this to be a linear function of x, of some transformed variable x on one side, and all right, in some parameters. How does that work? Well, you just flip it. 1 over y equals x plus theta 2 over theta 1x equals 1 over theta 1 plus theta 2 over theta 1 times 1 over x. Okay, now that's a linear function of 1 over x with transformed parameters. All right, so I transform y, I transform x, and I also transform the parameters. Okay, it's kind of all in one. It's the greatest simple example. Okay, so therefore, to get initial guesses of the thetas, I will just regress 1 over y and 1 over x. And that'll give me initial guesses of 1 over theta 1 and theta 2 over theta 1. And then I'll just solve those, and I'll get my theta 1 naught and my theta 2 naught. So if I regress, I'll just tell you the answers. If I regress 1 over y on 1 over x, what do I get? I'll just tell you what I get in this data. I get 1 over theta 1 hat, okay, equals, what's the intercept? Intercept equals 1 over theta 1 is 0.005107. Okay, this is the intercept. Okay, and I get theta 2 over theta 1 hat equals 0.0000247. How many zeros? No. Yes. Yeah. 1, 2, 3, 2, 4, 7. Okay, so that's the slope. Okay, so now you can easily, now it turns out you can solve these two equations without the hats for theta 1 and theta 2. So it gives me theta 1 0, therefore. That's going to be my initial guess of theta, is just solving this equation. 1 over the 0.005107, and that comes out to be equal to 195.8. And I get my theta 2, therefore, is equal to 195.8 times the 0.000247, which comes out to be equal to 0.0484. Okay, so those are my initial guesses. Now, the authors said that they followed this Puromycin data with some other initial guesses, namely of the initial guess of theta 1 is 205, and the initial guess of theta 2 is 0.08. Well, the 205 looks pretty much close to our 195. And the 0.08 doesn't look that close to the 0.05. But I'll show that we actually converge to the same answers that they have with this process. Okay? This is a little game. Okay? So they don't actually show the calculations I'm going to show. So let's just go ahead and go through this thing and see what we can get. Okay. So let's turn on the TV here. Okay. I think I still have the lights off. Here's the original regression of 1 over y and 1 over x. Let's just look at the residuals of ordinary regression of 1 over y and 1 over x. Since I get such a nice linear model, by transforming the regression equation, I should at least check out what do I get. Residual plot for the regression of 1 over y and 1 over x. Okay, well, residuals don't look like a flat horizontal band. Okay. So it looks like the variance is not constant, and also there's some nonlinearity. In other words, I don't have the right fit. The regression function itself, the original regression function, is nonlinear. So by choosing the thetas maybe differently, hey, maybe I could, fix this thing up. So there's the normal probability plot. Okay, so what am I going to do? Okay, first, there was the data that I needed in order to get my initial values, and there are my initial values already calculated on the board just now, 195 and the 0.048. Okay, now what do? I plug those in. I didn't calculate the derivatives for you by hand. Maybe I should do that. Pull the screen up just a little bit and show you what is going to be done. Okay. Just have to do the calculus. What's the calculus? Calculus is I have to do the partial derivative of f with respect to theta 1 equals d by d theta 1 of theta 1x over x plus theta 2. Well, that looks pretty easy. I think we can give that just about to any of our students. X over x plus theta 2. Okay? That's the first variable, therefore. That's my z1, or I call it z0, following the text. Okay? As if there was supposed to be an intercept. Okay? Playing the role of the intercept. Alright? Just the first derivative. Derivative with respect to the first parameter. Then I have df d theta 2 is equal to d by d theta 2 of theta 1x over x plus theta 2. And again, that's easy derivative. Theta 1 and x go for the ride because the derivative with respect to theta 2. And I get a negative 2 power from the negative 1 power by the chain rule. So I get a negative theta 1x over x plus theta 2, the quantity squared. So this is my variable z1. Okay. How do I get an actual variable out of that? How do I get rid of the thetas? I plug in my initial values. Okay, so Z0 at the 0th iteration, if you like, if I want to put in the full premises. I didn't do that in my worksheet. Therefore, is equal to x over x plus theta 2 at 0. So that's a number now, and then my x values stuck in there. And then I have zeta 1, or Z1 at 0th order is theta 1 at 0th guess x with a minus sign out here over x plus theta 2 of 0 squared. Okay, so these are fairly easy to calculate. And so I do. There they are. And there are the formulas just standing there. And I calculated all those. I also calculate f of 0, which is theta 1 of 0x, just my original regression function over x plus theta 2 at 0. So that's my fit. I did put the parenthesis 0 on that one, just to indicate that's my fit. And so that should be close to what the y value is. My fit is 57 at the first value of x, and my y, I lost it. Make this bigger now. Okay, bring the screen back down. My initial y was 47. Okay, so I have a residual of negative 10. My estimated residual is negative 10. It's my first guess of what the residual will be. And so there are all the first guesses of residuals. I actually take the sum of the squares of those residuals. They call that S of theta 0, where I put the italicized theta to indicate the whole vector. Okay? And then I went on down here, and now I'm going to regress E0 equals y minus F0, those estimated residuals, onto these two variables without an intercept. And so there it is. This is the no intercept business. Okay, NA. See what's going on there? I did show how this was done last time. So then I'm going ahead and getting the B's, or I call it beta 0 here, the B's. If I show you sheets like this on the exam, I'm not going to call them anything. I'm just showing it here because that's the notation that was in the book. Right? The coefficients are the increments of the thetas. Yeah. So then I have to go ahead and I have to take these coefficients and add them to the previous thetas. And you get 195 plus 15 is 210. I get 0.048 plus 0.013 is 0.061 now. Okay? And that's it. And now that's going to update all your z's and stuff. So I go and I go ahead and calculate them. Second iteration. Update what the z's are. The same formulas, but now put in the different thetas. Same formulas for the derivatives, but put in the different thetas, and I get the different two columns, and I get my different fits, and then I get different errors, therefore. Okay? And now my sum of squared errors is 1207 instead of 1900. Okay? And you do this, let's do it one more time. Let's see, I think the third iteration is somewhere else. I don't know where it is. Third iteration. Okay? This time I come down here, what are my changes now? Okay? My B's are getting kind of small. Why is that? That's good, actually. The B's are getting small means I'm getting convergence. That is, my residual vector is not going to be changing much. My thetas aren't going to be changing much, right? And in fact, since the B's are almost 0, the predicted output of this regression, which is basically giving how much the residuals are going to be changing by, okay, is going to 0. We'll do one more iteration. Predicted values are almost sent to 0, but not quite. Okay, all this column of predictions, those are almost all zeros, corresponding to these almost being 0. Okay? And so I'm going to do one more, and I go over here to the 4th iteration. Okay? And just do it one more time. And my S of theta doesn't change. It went from 1195.6 to 1195.45. Okay, so I quit. And my coefficients, my B's are very small now. Okay? Yeah, and I get the same answer that I got in the book for my actual final thetas then are, well, what are my final thetas? I can't remember. Where did I stick them? Okay? Oh, I guess here they were. This was close enough. I think I just took these right here, the theta 3, the 3rd iteration ones, and I just said those are the answers, 212.66 and 0.0641. And that should fit pretty much what they had in the book here in example 12 too. Okay. Any more comments about this? Could be one more thing we could say about it, and that is you can actually come up with F statistics. I'm kind of loath to talk about it, but I will anyway, to try to help clear up what's going on here. So there are my final fits, and there are my and let's see. So there's the residuals now. If I actually plot these things, all I did was plot, what did I do? It must be a column of numbers F3 and E3, right? I just took these F3s and E3s that were right here. Okay? And I think, or actually I should be able to highlight this graph and show that those are highlighted. Let me see, is that right? I forgot how that's done. You should highlight those columns there. Yeah, there they are. Okay? Took the F3 and the E3 and I made the graph. Okay, so those are the residuals. So they look halfway decent. Maybe one outlier over here. Okay? You've made the normal probability plot. Okay. And then there's the original data and the curve. In terms I just stuck the fits in there and made a curved line with Excel, or not so curved line, as the case may be. All right. I believe those values of the parameters 212 and 0.064 is exactly what the author came up with. It was a slightly different initial condition. Yeah. Page 426, he's got them written down in the second display from the bottom. Only he's got the errors in the book on page 426. He's put the exponential model in there. He just stuck the right parameters in with the wrong function. So he's kind of getting a little confused there. He thought he put the exponential function in your exercise, which is what 12.8 is. So you have to come up with, you're supposed to come up with an equation in the end that looks something like this on page 426. And your exercise only, of course, different parameters, different data. So he should have put y equals x plus theta 1 hat over, theta 1 hat times x over x plus theta 2 hat. He put the wrong function in here. Okay? And both that display and the bottom display on that page 426. Got a little bit lazy there. Proofreading, I think. That's not that bad of an error, but everybody see that there's an error there on page 426? Okay. Because the pure Meissner function is the theta 1x over the x plus theta 2. All right. Okay. So what else do I have here? On the notes, I've done something else. It's not on this worksheet. It turns out that the variance of theta hat, there must have been one more thing I put on this worksheet, is about sigma squared times z prime z inverse, okay? Where z is the last z matrix you made. So you made z equals to z0, z1, and so on, okay, as columns, all right, and so on, n by p, for p the number of parameters you had, okay? I think we just had 2 columns in this example. So, and this would be the final versions of the columns then, okay? So this is a large sample theory. Where theta hat is the nonlinear regression estimator that we came up with then. So that consists of, in this case, so we're talking about the variance-covariance matrix, the variance-covariance matrix of theta 1 hat, theta 2 hat, where I'm calling them hats now when I finish, okay? When I finish this process, I got the theta 1 hat is the 212.7, and the theta 2 hat was a 0.0641. But those are random variables, and as random variables, those are just numbers we came out from this data set. If we take in a different data set, we'd get different theta 1 hat and different theta 2 hat, right? So you can imagine just a whole bunch of theta 1 hats and theta 2 hats. Remember the simulation we did? Okay. Just one row of theta 1 hats, one row of theta 2 hats. Now, what's the variance, the theoretical variance of that row of theta 1 hats? So I'm not going to redo millions of experiments to calculate the variability of theta 1 hat. All right, I need a nice theoretical expression for it. And it's approximately the 1-1 entry in this variance-covariance matrix. So, so that's going to be the variance of theta 1 hat, the variance of theta 2 hat here, and then I have the covariance between theta 1 hat and theta 2 hat. That's what the variance-covariance matrix is, and that's supposed to be, that's sigma squared times this, right, times z0, let's see, it'd be z0 prime, z0, z1 prime, z1, and then z0 prime, z1, z0 prime, z1, or z1 prime, z0, I don't care. Inversed, okay? So you take that matrix and you invert it, okay? Where sigma squared is going to be also the MSE from your last. Let's see, what is that going to be? No, that's going to be your, where your sigma squared is going to be, your sigma hat squared is going to be your S of theta hat divided by n minus p. Where, remember, I was taking the sum of squares of these these residuals that I got from the nonlinear fit. And so that's what I'm going to use that. Sigma hat squared is this. So that came out to be 195 divided by 195.45 or whatever divided by how big was n in the pure Meissen data? I can't remember. That never came in very much. N was 12. P was 2. So this came out to be 12 minus 2. So you get 19.545 for the sigma squared. Okay? Now, one thing I didn't do is I didn't actually compute the inverse of this thing. So you'd have to do that. And he did calculate sigma hat squared. Did he actually do? All right, he did not actually do that. So you can see this. I'm sorry, 119. This was 1195. I'm sorry, 1195. This came out 119.545. And then he went ahead on page 429 and calculated the variance-covariance matrix at the final value of z. Let's see that we get the same thing. Let's go ahead and calculate. Remember how to do that? How to calculate the Variance-Covariance Matrix. Let me take my last Z. Where is the little devil? Up here. That's close enough anyway. Okay? I need to take these two columns and call them something. I might as well call them Z. Okay? All right? Enter. And then I'm going to go over here and do the calculations. Give me a nice little space here. Okay, so I need capital Z prime Z. So I need a 2 by 2 matrix equals M mult transpose of Z with Z, shift and all that. Shift enter, whatever. There's Z prime Z, and then I need the inverse of that. So give myself a 2 by 2 array. Come on. And well, maybe I'm going to put it here. Equals M inverse of this 2 by 2 array here. Close parentheses, shift control, enter. Okay. So which one is he trying to calculate? He's trying to calculate the standard error of theta 1 hat. Okay. So he's taking this 0.4036 or whatever you got right here. So the standard error of theta 1 hat, okay, is therefore equal to, it's the 1 it's just the square root of, okay, it's the square root of the 1 try this again, square root of the 119.5 okay, that's the square root of sigma hat squared times the square root, well, I might as well just make it the square root of the whole thing. It's the square, because the square root of this thing times that number there. That number there. Standard error is the estimate of the standard deviation. We calculate the variance of theta 1 hat is the 119.5 times that number 0.4037 or 0.4036 as it shows here. So you get the 6.9, which is what he got. Okay? Bottom of page 429. So we got exactly the same results. All right. I hope that you're happy with that. Is there an F statistic? You couldn't read this very well with the light on, could you? Could you still read that? What did you do? You just didn't tell me.
Well, I just used the cameras.
Oh, good.
So you're invisible, but everything else is.
Oh, that's good. Whether the fit was significant or not, he's got a stat graphics nonlinear regression output. He's got some other statistical software shown in here and so on. The main thing about the comment that I'd make here is that when you actually do the nonlinear fit, the concept of an intercept sort of goes out the window. In other words, when I write down the normal equations, there is a normal equations too. And they're approximately satisfied with this theta hat. What do the normal equations look like? I think I'll take this thing off now. So in this nonlinear regression, you have the normal equations. And they would be what? D by D. What is it in the, remember what it was? You take the S, which is the sum of the squares of the y minus the regression function, f of xi theta, okay? You square it, that's your S, and you try to minimize it. So you get the partial, you take the partial of S with respect to theta 1, you take the partial of S with respect to theta 2, is that equal to 0. I'll just take 2 thetas, that's enough for now, okay? And what do you get? You get summation y minus f of x I and theta times the partial derivative with respect to theta 1, okay, at x and theta, okay, equal to 0. And there's a factor of 2 and a minus sign. We'll just put it down here. I goes from 1 to n. And you get a minus 2 summation I goes from 1 to n. yi minus f of x I in theta times the partial derivative of f with respect to theta 2 of x and theta equal to 0. And these, when I put in my theta hat, this is just z 0 and this is z1, right? The columns of the z matrix. So what you're getting is that you should have that y minus. What you should get is that, and this is just the this is just the residual, okay? So you're getting y minus. So you're getting the residual basically. E is perpendicular to z0, and you get an E is perpendicular to z1, okay? Which is approximately true. Now, because well, we could check it out, I guess. That's what you're getting from this minimization problem. Should we check to see if it's true? Let's take this E3. Let's just take it. I don't think I calculated F4 and E4, but if I just did it with this, if I just take, I even take Z0. Oh no, I'm off the screen again. Darn it! Keep running into this thing. Okay, let's leave this thing down. Let's just make sure everything is kosher here. What's the inner product of F3 and E3 and Z0? Right? This is Z0 of 3. This is the third. This is the column of Z in the final K, and this is the final E. Is everybody following me? So I want. This is the first column of Z. That's the Z0. This is the second column of Z. That's the Z1. This is the E vector. Okay. So let's see if it's about 0. Okay, how do I take the inner product? Equals M mult. I need the transpose of Z times E, right? That'll give me a transpose of Z0. So I'll just put that in there. This is my Z0. Okay? And then times E. Oh, no, I could just multiply and add too. Okay? Times this one. But this is just as fast. Okay? Alright, well that's pretty close to 0. Looks good enough to me. Okay. And if I take that one, transpose of Z1 times E3. Did I spell it? Good. Okay, thanks for catching it. It'll kill me for that. Okay. And then I close the parenthesis. Shift alternate delete. Uh-oh. That didn't work. Maybe I really did spell it wrong. That's not so close to 0. Okay. Because I still have big numbers in there. Okay, I might have to go to E4 and to really get it to be 0. Okay, you can see the numbers are awfully big though. 601 down to 172, and I'm multiplying by things between 6. So if it was, sort of the typical average value, if it wasn't coming out to 0, it would be something like, a lot. 10 times 3,600, or 10 times, a couple thousand. It should come out 20,000, and it came out 48. So that's pretty close to 0. Okay? If I did one more iteration, probably, or if I had shown the iteration, then it should be close to 0. So, believe it or not. All right, so those are the normal equations. And so what am I getting? I'm getting a picture that, so I have y, and I have e, and so I have some stuff here. I have some kind of right angle. I have my fit vector, right? F, and I have my E. What do I have? Yeah, I have my fit. This is my fits. My fit vector, and here's my Y vector, and here's my E vector. And E is approximately perpendicular to Z0 and Z1, and but is F itself a linear combination of Z0 and Z1? I don't see that. Maybe I have the picture wrong. I'm going to have to punt here and tell you next time the rest of this picture, I think. Because it's kind of not clear. He doesn't make it clear in the book, and it's not totally clear to me. Where does F lie? Is F a linear combination of Z0 and Z1? Is it that simple? That's simple? I don't think so. Let me check that out. What's my theta hat? .0. Okay, my theta hat. The theta hat was the. F is a linear combination of theta 0 and theta 1? In terms of the z's? Maybe it works down to that. Let me see. Let me just check that. In our example, we can easily check it. What did it come down to? We actually calculated F with the original formula. Okay? And the way the z's are defined, let's see, the z's would be defined, let's see, would it make sense? No, it wouldn't make sense. Only the last increment of theta, which is where all the variability is, you might say, okay, would come into that. In other words, you sort of think of F as frozen close, okay, and then the variability in the thetas, okay, would be written as a linear combination. Let's see, the variability in F would be written as a linear combination of the thetas. Okay, so it's not quite right. So what you get, so this is, F is not in the span of Z0 and Z1. Okay, I don't believe. Okay. I could check that. I could just take Z0, Z1, and F as 3 columns and try to see if I could invert the matrix where I get by the X prime X matrix where I actually add F3 as an extra column and see if they're linearly independent. Okay. Okay. I'm sure that won't be far from true. Okay. So I don't believe that this is a linear combination of those two. But what you can still say that anyway, I'll try to clear that up a bit next time. Okay. E is perpendicular to Z0 and Z1, but not perpendicular to the fits. Okay, I could check to see whether E is perpendicular to the fits. If I did the same business as, I don't know, can I change an array formula? If it was perpendicular to Z0 and Z1, it should also be perpendicular to the fit, right? So if I put in, instead of J107, I put in the N107. N107 to N118. Okay. Oh. Maybe it is. Okay, well, it does look like it is perpendicular to the fits, too. So I guess I might be wrong. Okay, so this is correct. All right, okay. Yeah, I do have that written down. I've got SS model. I have this SS model is equal to summation fx theta hat squared, which is just the square length of this vector here. And then I have, this is perpendicular. So why did I mess that up? Okay. Okay. And I do have that, and then I have, this is S, this side has SS res, okay, theta hat, okay, or S theta hat, we called it, we didn't call it SS res. And then I've got here summation yi squared. Okay, so the total sum of squares is not corrected. All right, then what you get is that under null hypothesis, that the regression function is trivial. He says if the thetas are 0, but really you should write it as the assumption that the regression function is identically 0. Okay. Then what you get is that under this hypothesis, then S theta hat divided, well, see now, it would be SS model divided by S degrees of freedom divided by P over sigma hat squared, which would be S theta hat divided by N minus P. This would be roughly FP N minus P. Okay, so you could test the hypothesis that the regression was trivial. But you'll always reject anyway. I mean, there doesn't seem to be much point here. So this theory doesn't seem to be too helpful. Because there's no testing that one of the parameters is trivial or something here. So that doesn't seem to be too useful. Okay. Well, anyway, there's nonlinear regression. I think we've gone through a time and a half now. So next time I'll spend a little bit of time on logistic regression. So dip into chapter 13 a little bit, but I'm not. The author really gets off into like other statistical softwares and so on. It pretty much doesn't even talk too much about how you would do it by hand. Which one of the students was complaining a little bit. I never learned how to do it by hand, you know. And so I apologize to some of you if it took you too long to struggle to do that, to figure out how to do things by hand. But I am going to be asking you to do things a little bit by hand on the final. So if I ask you to go ahead and do a simple linear regression on the final, would you be able to do it? Would you actually be able to go through all the calculations? Go through the normal equations and solve everything down and so on. That's one thing that might be a reasonable question. Usually, I think in thinking back on this course, I usually gave that first chapter, the first problem in the first chapter, like 2.4, maybe 2.9, where you had to compute the prediction bands and so on, or confidence bands, do it all by hand. So if you're feeling like you really never learned how to do that by hand because of the computer, there may be more than one person who thought that way, okay, then I recommend going back and picking that up, trying to do some things by hand. That might help you prepare for the test. Just go through problem 2.4 and do it all by hand. I'd say it would probably be a good exercise. Okay. And maybe that'll be my extra credit problem. Just say, do this problem by hand completely. You know? All right. You're welcome. We'll see you tomorrow, last day of class. And I don't know if we're going to have the student reviews tomorrow, because I don't know. Joni went out of town, and I don't know if she prepared them for us by tomorrow. So we may actually have to have those on the final exam date. I apologize for that. It's not. I don't like doing it then, and it's against the rules to actually do it then. But there may not be any other choice. So.